All right, so the picture that we have down here is a picture of a kick in soccer. I've put the video above this one on the page, or if you're looking at this somewhere else, you can just look up a video for Magnus force. And we're not talking about that force, but you can see in that video something really weird is happening to a ball that's moving through air. It actually curves in the air, and the reason why that's happening is because the ball is spinning. So that's a little bit strange. And the point that I want to make with that is just that the forces that air can put on an object are complicated. Usually, if we're just standing in air, we don't feel forces pushing us to the side or slowing us down. But that can happen. And so we're going to talk about drag forces. Those are the forces that will generally slow you down. And the drag force on an object through any sort of fluid, not just air, depend on the speed. So if you're going faster, that means it leads to higher drag force. If the size is bigger, that's also higher drag. And also the shape of an object can affect the drag. So a dolphin is streamlined, or a really cool car is streamlined so that there's less drag and there's less air pushing back on the car, or fluid pushing back on the dolphin, so that it can go faster. So there are two kinds of drag forces. There's viscous drag, so here we have viscous drag, and there's also something called pressure drag. So viscous drag is when you're in something sticky, or the thing that's moving is in something sticky like honey. So you can imagine, for example, a ball or this little apple. If it's moving through, say, honey or tar or molasses or something like that, you can imagine all the particles are sticking to the apple, the particles near it, and those are sticking to all the particles next to it. And so if this starts moving, then it wants to drag all those particles with it. And so what you'll get is a slowing down of the object because it's trying to drag all these particles as it moves forward. So this is also why, if you pull a knife out of honey, some of the honey comes out because all of that honey is sticky. So that you can see that when you're not in a bunch of fluid, the honey is sticking to the knife, but that also happens if the knife or a ball were moving through that honey. So that's one kind of drag force. The other kind of drag force is pressure drag. So if you're in air, usually there isn't a lot of viscous drag, but there can be pressure drag. So you might have experienced this if you're running, or if you're on a bike, or if you're standing on a car while it's going down the highway. You feel a lot of pushing on the front of you, and that's because the pressure is higher on the front of you than behind you. And that's just because you have all these particles, and there are just more bung, 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 bung hitting the front of you than are hitting the back of you. So we have a high pressure here, if we're moving this way to the right, and then a low pressure over here. So there are also equations that tell us how big these forces are. So the magnitude of the viscous drag force is proportional. So we know that how this scales, how this gets bigger with different quantities. And I'm not writing an equality, but we'll get there. This is proportional to the viscosity times the velocity the object is moving times some length scale. So this is the Greek letter eta, and that just means if you have something that's more viscous, more sticky, then you'll have more of this viscous drag. Then also it makes sense, I was saying earlier, that the drag will increase if the speed goes up, and also if the size of the object goes up, then you'll have a bigger drag force. And we'll often look at a sphere because there's something called Stokes' law, which describes what the drag force of a sphere is. So for a sphere, we have F viscous drag is equal to 6 pi eta, it's the viscosity of the fluid that the sphere is in, times the radius of the sphere times the velocity. And so we'll be using this to figure out, let's say you have a vesicle that's going through some fluid. You can figure out what the drag force is because say it's in water, the viscosity of the water, the size of the vesicle, and we'll tell you how fast it's going, so you can figure out how much drag force there is. Then, of course, there's this pressure drag. And pressure drag doesn't depend on viscosity, but instead it depends on, so this is the Greek letter rho, it depends on the density of the fluid. So if the fluid's more dense, then you'll get more of this pressure drag just because the thing that's causing pressure drag are the particles hitting you. If there are more particles per unit volume, then that means higher density, and that means that if you're moving through the fluid, you're going to have more particles hitting you on the front than the back. So the difference in the number of particles hitting you is going to go up if the density goes up. So we also have a law that explains this. Let's first do the proportionality. So for pressure drag, the force is proportional to the density of the fluid times the velocity squared, and then some length scale squared. And so, and then that might be a little confusing when I say length scale, but we can also write this as the force of drag is equal to 1/2 times c sub d, and this is just a drag coefficient for a particular object. So if we have some object, we'll say the drag coefficient for that object is 3 or something like that. And then we have here the density of the fluid, and then A, which is the cross-sectional area of the object, and then times velocity squared. So, for example, this cross-sectional area, you can see what it does if you just imagine running, where let's say you're running straight and you're putting your arms out, or let's say you have you're holding a big cardboard sheet or something like that. You're increasing the cross-sectional area, and so that means that the pressure drag is going to be higher. And so that's how the size affects. That's one way the size will affect you in the pressure drag. Also, you're very greatly affected by the velocity because the drag goes up by the square of the velocity for pressure drag. And so you might be looking at some object moving in some fluid, and you might wonder, okay, is this a situation where I should think about viscous drag, or is it a situation where I should think about pressure drag? Well, usually the viscous drag, so up here, this usually refers to microscopic objects. And then this, the pressure drag usually refers to big objects. So in air, if you had something really small, there could be some of this viscous drag, or if you're in water and you're small, there could be viscous drag. But if you're big person that's in air, you're going to be experiencing pressure drag. You'd have to be in something really, really viscous, like tar or honey, in order to feel this viscous drag as a big object. So that's just an introduction to drag, and so we'll do some examples in class. I hope that was helpful.